So now what I wanted to do is that I have asked you to download from this website some code files like simulation of turbulent flow in a 2D channel. I have asked you to download these code files. So you go to that specific location where you have your downloaded code files. So actually, I had my in the download section, and I had extracted this on this. So this is our case. So you can see that in the constant folder, we have another folder called turbulence properties. So I think you have basically gone through the downloaded code files that I had asked you to download, and you get inside it and go to kepsilon and go to a constant folder, and you can see that there is a file name called turbulence properties. Just copy this, Control C, and then you just paste it in your laminar folder inside the run directory. I think you get this. So in your laminar folder, you have constant, and inside the constant, there is a turbulent properties file missing. You just copy that from the downloaded code files and paste it here. Now you can see that we have two files, transfer properties and turbulence properties. Now I think we have the required files. Now see that if you do it manually, we can see that a new additional file is being generated. So you can just keep it or you can just delete this. So now we have all the required files to run our simulation for the laminar case. Okay. So now we have our template ready to run our simulation, but we can see that we had copied from the cavity case. So that if you go inside the system in the block mesh dict, this is not the actual block mesh that we want to generate our mesh. This is for the cavity case only. So we want to replace this with our with the downloaded ones. So if I go downloads inside the downloads and the code that I downloaded, that is simulation of 2D turbulent flow in a channel. So you just go inside it, and from the system there is a block mesh dict file. Just copy that, copy this, and then go back to your laminar case that is on the run folder. So you can just open multiple tabs and then switch on and switch this between these tabs like this. So you can see that now you can see that inside these laminar folder, inside the laminar folder in the run directory, there is the system, and system has block mesh dict file, but this is not the required file. That is the original file. So we want to replace this. So just paste it here. So now you have replaced it. Now if you open this, then you can see that we have replaced the original file with the new one inside the block mesh dict file. So these are that I demonstrated earlier. This is the block mesh file. Now you can see that additional file generated. Let's repeat. Now after our block mesh is ready, after we have copied the block mesh from the downloaded section to these laminar folder inside the run folder. Now just what you can do is, now go to your terminal. Now go to terminal, and after going to the terminal, type run. Yes.
Sir, in a constant folder, turbulence properties,
Yes.
we have not enabled laminar, right? Right now,
Yeah. We will change. Yeah. We need to change that. So right now we are doing turbulence. It is, I think, check turbulence. We will change it to laminar, but let me first create mesh. That teach how to create mesh, and then we'll see to it. Okay.
Sure.
Okay. So in a terminal, type run. This will get into the run directory. Now inside the run, there must be a laminar folder created. So just type cd laminar. So this will direct you inside the laminar folder. So I have, so you can see that I'm into this address, that is OpenFOAM Manjil 9 run and laminar. This is username. It will be different from mine. So Now because now our setup is ready to create a mesh, because we have copy pasted, like we have brought the block mesh files from the downloaded uh, downloaded code file to our original this working directory, that is laminar. So if you type block mesh now.
Uh, just a quick question. Can you show where to download that exact code for the turbulence one? From where to download?
So okay. So actually, it is available in the spoken tutorials website.
Okay, okay,
So
okay.
you can,
Uh,
and here in the spoken tutorials, you can see code files here.
right, right. Okay, right.
Okay. Okay. After you have done these for these steps, like you have created first, what we have done is we have created a folder called laminar. So inside after creating the folder, we have copied from the cavity case that we had already run. We have copied the zero constant and system folder from the cavity case to our laminar folder. Right, that was our first step. Now, after we copied from the cavity case to the laminar folder, that is not the required. There are not the required files inside the in this laminar folder. So what we did was we downloaded from the spoken tutorials website the required files, and then we copied those files, that is the block mesh files, into our system. That is, we replaced it with the downloaded ones, and also we added a file called turbulence properties in the constant by copying from the downloaded ones to the laminar folder. Now, you can see that after I run block mesh, a new folder called polymesh is generated. So inside the polymesh, you have this set of files. So you can access this later. So after you run block mesh, this should create a polymesh file inside the constant folder. Yes. So this is the now the important thing is you want to run a laminar case. So in this turbulence properties file, you open the turbulence properties files, which is located in the constant folder. Right now you can see that we have assigned the simulation type as RAS, which is runs model, but we want this to be laminar instead, because we are doing a laminar simulation. And if you do this laminar, then you don't have to delete this. This won't affect this. So we need to assign our simulation type to laminar. So this file is located inside the constant folder in the turbulence properties. So if you have this file missing inside the constant folder, then I request you to download to copy paste this from the downloaded code files.
Can you visualize the mesh?
Okay. So I think everybody have followed it till now. So let's now we have also created our mesh. So let's just type Paraform.
What
Okay,
will
what
be
did
the
you say?
simulation type? Uh,
Laminar.
Yeah, what
You
will
need
be
to,
the simulation type? Laminar. Okay, thank you.
laminar. You need to assign as laminar case. So you just type Paraform the dash built-in. In case your Paraform is crashing, sometimes it crashes. So I will refer to this command Paraform dash built-in. So you can see the command here Paraform dash built-in. So now you can see that now after a Paraform will be opened. Now you need to apply the green. You need to click the green button that is will be highlighted in green. Just click apply. And if you want to visualize the mesh, then you just click surface with edges. So now see that you can see that there is a grading applied here, right? So we have very fine mesh at the walls where we need to capture the boundary layer properly and the gradients properly. So you have, so why is this? Because if you go to your block mesh file, so if you go to your case, so so if you go to your run directory and laminar case, so this is my case, that is inside the run directory. I am going inside the laminar case, and inside the system, I am going inside the block mesh dict. So we can see that in the simple grading, we have applied a grading in the y direction, right? So, and if you visualize this, there is only grading applied in the y direction, not in the x direction, because we have in the x and z direction, we have just applied one value of uniform grading. But in the y direction, that is this in between, you can see that we have applied the certain number to this y direction to create a grading. So we have this amount of cells, 75 in 30 in the y direction, and we have applied this grading. So how do you calculate this grading? So that might be a question. So basically, this grading refers to the ratio of the last cell to the first cell. So for the laminar case, okay, I think we can stick with this grading for now. If you want to create a new grading, okay, let me teach you how to do it to create a grading. So if you want your first cell height to be okay, you have a first cell height. Let us create a first cell height with with the 0.002 meter in the first cell. So this will also help you in the turbulence case later how to make the grading. So you just go to your web browser and type block mesh grading calculator. I request everyone to go into this. And I think it is the first site that will okay, you must that after you type that block mesh grading calculator, there is a first website. So just click inside that, and now you can see that there is this interface open. Like you need to assign first you need to have the input parameters in order to develop the mesh. So what we have now is, so let's see this. So if you let's suppose that we want to create the first layer height with 0.002 meter, that is the first layer height would be 0.00 meter. So what we can do is we can just in the drop down option we can click width of start cell. So we can provide width of start cell, and then if you want to do a first cell height with 0.002 meter, just type 0.002. And there is an option called total length. So we have our length of 0.5 meters in the first block, because we have two blocks which is of 0.5 meter height, and the upper block is also of 0.5 meters height. So first we are doing for the first block, that is block 1, we are specifying the grading, how to do the gradings. And we have assigned the number of cells as 30. So you can see that in the y direction, we have assigned number of cells to be 30. And we have our the height as 0.5, that is the length as 0.5. This is just I'm doing it for reference so that it would be easy for to do setup in turbulent case. So if you do this, then you can see that total expansion ratio comes around 28. So this value is, that is the ratio of the last cell to the first cell. We can see that our first cell is 0.002 meter, and we can see that our last cell is 0.05 meter. So if you do the ratio of these two values, this would give the total expansion ratio. So in open form, when you calculate these grading parameters, it is actually the ratio of the last cell to the first cell. So you can just type it after you get. We have a total expansion 28, so I just typed in 28. Similarly, in the second block, that is in this block, in the second block, okay, we want our grading to be this way. That is, in the first block, we have the first cell as very fine mesh, but in the second block, we have the last cell as very fine mesh, right? Because we will start from this direction, from the y direction, while we have assigned the blocks. So we can see that in this block 1, our first cell is very small compared to last cell. But in the block 2, we can see that our last cell is very small compared to our first cell height. So now what you need to do in this grading calculator is, the number of total length is also fixed, the number of cells is also fixed, but instead of giving width of start cell, you can give width of end cell. And you want your first cell, that is in the so you want this first first layer height from the upwards direction in the block 2 to be 0.002. So I am doing keeping this as 0.002. 2 and press enter. So you can see that now the total expanse ratio comes to be 0.035. So because we have the last cell very small compared to the first cell, so while doing the ratio, the value is very small. So just keep this value 0.035 in your block mesh file. 0.035. So I have chosen to keep my first cell height at 0.002 meters, and accordingly I have calculated the grading parameters. So what we need is we need the length or dimension of our height or dimension of our block, and we need the number of cells, and then we can calculate it accordingly. So just press Control S to save the file. So I think you have you know now how to calculate the grading. So in this way you can calculate the grading, but in turbulent case, the y plus is not important. So I've just to make it fine, I've just used reference at 0.002 meters as the first cell height. So after you have done this, so you have edited this. You need to run the block mesh again, so that this effect will be incorporated in our mesh again. So let's go to terminal.
So can you please show the vertices once? Okay.
This is the vertices. You don't have to type this because it will take time for now. So I have just asked you to copy paste from the downloaded files. So if you go on typing this, it will take much time, which we will be on sort of time. So after this, just press go to terminal. If your paraform is opening, close the paraform, or you can just press Control C in terminal itself. This will close the paraform. Control C. Now run the block mesh again, because we have changed something in the block mesh and we want this to be
Sir, how I
incorporated.
can go in that laminar terminal actually? Because my internet got disrupted. Right now, when I'm typing ls, it is showing that is in cavity case, laminar, and pits daily. So different
Go type CD laminar. It will get inside the laminar folder. CD laminar.
terminals are there. How I can go to laminar? Okay, no space.
CD space laminar.
Okay. Okay, now I'm in
So
laminar.
so you have not copied from the downloaded. You have
I
missed that part?
copied. I copied that mesh thing from
Okay, fine.
silent file. Yes.
Okay, fine. So that's okay. So after you edited that part, just type block mesh.
Okay.
So what I changed was that I changed the grading, and I also taught you how to change the grading. So you
Yes,
can
sir,
always
yes.
refer to this later. If because if you have on your free time, you can do this. So I have chose the first cell height to be 0.002 meters.
Yes, sir.
Actually, we don't have a y plus value in the laminar simulation, so I have chosen an arbitrary value of 0.002 meter, so that y plus will be equal to 1 or something like that. Okay, after you do this, just run block mesh, and then you can.
Just one quick question I wanted to know that about the. Can you show the script of the block mesh? Yes. This the way the cells are arranged in the hexagonal. Can you tell me it is I need to arrange it clockwise, and these two hexagonal segregation is for the two blocks, right? And so it will be
Right.
segregated according to the number of domains, or if the geometry has many different domains to be simulated, then I need to segregate in different row. And so, can you tell me how these cells are segregated? The 0, 1, 3, 2, 6, 7, 9, 8. Like, is it clockwise or like?
Okay, I think you have missed the session
Yes,
before.
yes.
So actually, Ivan has also demonstrated that. Okay, I will tell you once again. Then what you do is,
Okay.
so this slide.
I got it.
So you can, okay, 0, 1. You either go anti-clockwise or you go clockwise, but it should be the same convention.
Okay.
Okay.
Sir, after doing block mesh, I have to do icoform, right?
No. We are only at the block mesh now. We are not running in the simulation. We are just creating mesh, generating mesh for now, as of now.
Yeah,
Yes.
actually, my terminal got closed. Can you show me how to navigate to laminar?
Okay, just you type open
Laminar.
here Ubuntu. after you run Ubuntu, after you launch your Ubuntu, then just type run. Okay, this is okay. I have to alias it first. So after this, type run. So you'll be directed to the run directory. Now inside the run directory, you have your laminar case, right? So type cd laminar. This is telling you to go inside the laminar case. So in this way, you can direct yourself to the laminar folder. Did you get it?
No, it's showing no such file or directory.
Okay, so I think you have not created laminar folder. So
I
if
think
you
so.
type, okay, I think we have missed that part. Okay, we'll come back to that later. So just if you type ls, then there should be a folder called laminar created.
Okay, no, it's not showing. Only the run file is
Okay.
showing.
You have just joined now, or you have from before?
No, I joined 15 minutes ago.
Okay, fine. Okay, so what you can do is first of all type this command mkdir laminar to create a folder called laminar.
Okay. Yeah, done.
So now if you do ls, then you have a laminar folder created.
LS, yeah, laminar, yeah.
Yeah. After that, you what you should do is now inside the laminar. So right now we have already created our mesh. Now you will see the boundary conditions. So what you just open your file explorer, go to the run folder, go to your laminar folder. The run folder is located in Ubuntu. So you just go to the run folder and go inside the laminar folder. And inside the 0 folder, you have boundary conditions for P and U. Right. So what we can do now is we just can, because we are short on time, so we can copy from the downloaded code files the P and U files inside these boundary conditions. So what you do is you go to your downloads folder, and for where you have downloaded your code files from the spoken tutorials website, go inside that, and you go inside that. So actually, even it is a KF silent case, the mesh is same, the domain is same. So we can only change some parameters to change it from laminar to turbulent case. So actually, so I'm I'll just transition from laminar to turbulent case in this way. So we do not need epsilon k nut for the laminar case. So just copy the p and u file. Just copy this p and u file and paste it in your laminar folder inside the 0 folder. So go to your laminar folder, go inside the 0 folder, and then paste it here. Okay. So now you can see that now I want you to open the U file inside the laminar folder. Open the U file. So you can see that we have assigned the inlet as for the U velocity boundary condition. So we have assigned velocity boundary condition at the inlet. So it is a fixed value of 20 meter per second. But what I had shown you in my presentation, that we are doing a laminar case of Reynolds number 500. So we want our average velocity to be 0.005 meter per second. This is for turbulent case, right? So now we want to change it to 0.005. This is for the laminar case. So I have actually taken the files from the code files of the spoken tutorials website. That is done for the turbulent case. Now I'm changing it to laminar case. So we are operating on the Reynolds number, which is in the regime of laminar, in the laminar regime, and the value of the average velocity is 0.005, which I have calculated using this formula of Reynolds number. So after you do that, you have provided a fixed value at the inlet. So you have provided outlet 0 gradient boundary condition. The 0 boundary condition, what it does, it takes value from the nearby cells and keep it as its own. That is, the gradient at this outlet is 0. So what is near to the cells, what is the value? It will take the values from that cells only. It won't calculate. So we have assigned upper wall and lower wall as no slip boundary condition. I think you know what is no slip boundary condition. And always keep in mind that this syntax, that is these capital letters are very important. That is, you need to always worry about this capitalization. That is, the first one is zero, the first one is small letter, and this one is the capital letter. If you miss this, then this will give you errors. So, and we can see that we have our front and back as empty because we are doing a 2D simulation. Okay, now our this is ready. Our U boundary files is ready. Now let's go to the P files. Okay, you can keep the P files as it is because we don't have assigned any values. So actually, in the outlet we have the fixed value set to atmospheric pressure. So you need to do this. So in the inlet zero gradient boundary condition, we calculate from the velocity itself. So upper wall, lower wall, and front and back as empty in both these U and P files. Okay, now this is our boundary condition is also ready. Our transport properties, let's see what is inside. So it should be, you can see that the kinematic viscosity is set to 0.01. But in our case, the kinematic viscosity will be 0.18 minus 5. So you should also change this value. So let's change this value. So now we have set the value to 1e minus 5. Yeah, I think you got this. Okay. So we have also changed the turbulence properties as laminar, as also fine. And in the system, now what I want you to do is you just paste all these contradict FE schemes and FE solution from downloaded files, from the downloaded code files. So just copy this contradict FE schemes and FE solution from the downloaded from the code files to your run folder where there is laminar case. Okay, here is my laminar folder inside the run directory. So I'd like you to copy this. Okay, so you can delete these extra files. This is the artifact of doing it manually. So you can now we have all the files ready. We have like edited the tolerance properties file, transfer properties files. We have also made the PNU, set up the PNU boundary conditions. Now let's look at the control dict file. So in the control dict file, you basically have to assign the start time, end time. And always note that which solver you are using. We are using here simple form, and simple form is a steady state solver for incompressible and enclosed with turbulent flows. So we are using a steady state solver. So actually the end time and this delta T do not matter in the steady state simulation, but to match with the framework of OpenFOAM, this is used to just match the framework with the other code files as well. So this is the right control, right time. I think Ivan has already explained this how to set up these values. So actually simple form is steady state solver, but this time step is not important. But what is important is okay, this is the discretization schemes. They are the FV schemes. So how do you discretize the temporal schemes, the time schemes that you are using steady state? If you are using a transient, then you must assign it as Euler. That is Euler for the transient simulations. So these are for the simple form. It is just steady state. So these are the the divergent schemes. So how do you discretize this? So these you can go to it later. And then FV solution. So in the simple algorithm, this on the relaxation factors is very important because this will have to help in stabilization of the solution. So you should set these values and study about these values properly, because these values will decide on how much you want to change the gradient and get the new value. So this relaxation factor is very important in the simple form. So I think we are already ready with the files. So I've changed all these required files. So now let's run the simulation. Okay, let's go back to our terminal where I have run laminar case. So as I'm using simple form, I have already run block mesh. So I'll type simple form. So it says transport properties. Let me check it.
Manjil, you copy the transport properties from the setup only because
Okay,
because
fine.
this
So actually,
cavity case was for icofoam, right? That's why the
mm,
file structure is different. So you explain to them that the file structure is different and copy them. It will work.
mm, mm. So what you do is we had copied the turbulence properties file from the downloaded files, but this transport properties file was copied from the cavity case. So this is creating this error. So what I want you to do is just copy the transport properties file from the downloaded code files into our Laminar folder. So go to your home, go to your open form, and then run folder. Go inside Laminar, constant, and then paste it here, replacing the old transport properties files. So you can see that this is quite okay. You can see the syntax is different. In the previous one, we had not assigned transport model as Newtonian, but this and it was in the error. We can see that it was asking for keyword transport model is undefined. Now we have defined transport model as Newtonian. So we have resolved this error. So you need to see the errors and then fix it accordingly. Now if I type now if I go back to the terminal and then type SQL form, now you can see that the simulation is running. So just type capital F and you can press tab. It will you don't have to type it all. So we have so our simulation is complete. It has come to the end. Okay. So you can see that in these folders that inside the laminar you have created these additional datas are stored here. So in simple form, it will stop when the simulation will convert or when it reaches the end time. So after the residuals is also very important. So in the FB solutions, there is there is a tolerance. Yeah, I think this is the residual tolerance. So after it reaches the residual reaches converges to these values, then the simulation will stop, or it will stop if it reaches the end time. We have our files ready. So now let's visualize in the Paraform. So let's type Paraform built-in.
Sir, I'm facing issue with like simple form while running the simulation.
What is the issue?
So it is showing that a form fatal error actually cannot find file laminar 0 nut karke is there.
Which file is missing?
It is showing that Ismail run laminar 0 nut cannot find file. It is showing form fatal error. It is showing laminar.
NUT is missing, Manzil. I
Yes,
think
yeah,
he
I
has
know.
not replaced the
Hmm.
what you can say RAS to laminar in the turbulence properties.
Okay.
Which files?
So so you need to replace the why you so you go to your
Transport as
laminar
well. Okay.
transfer model is missing.
No, NUT is missing something. NUT.
Okay, so what you have not changed is So you go to the constant, inside the constant, there is a file called turbulence properties. So just open that file in your laminar folder.
Yeah.
And have you set it to laminar?
Which one I have to supposed to set
You can
laminar?
see your simulation type as laminar. There is
Simulation type
RAS.
RAS is there, yes.
Okay,
RAS is
you just change it to laminar.
okay. In place of there is no hyphen, right? Laminar.
No. So because we are doing a laminar simulation, so we must change it to laminar.
Okay,
Okay,
small
fine.
line. Small line.
Okay, after this, then you can run
Yeah.
the case.
Okay, simple form. Okay.
Okay, so what you can do is basically you can copy all these downloaded code files and replace with these test cases. That would be easy. Instead of copying one by one, you can copy all at first, then you can run the simulation.
It's running, sir. It's running now.
Okay, fine. So let's view in Paraform. So after I click apply, so you can see that our result is ready. Okay, so I'll only demonstrate one thing in this para view. So apart from that, you just learn to post process on your own. So let me plot a value. Okay, I'll show you. So I will plot a line in this domain and see the velocity variation along the y direction. That is, I want to see the boundary layer formation. So I want to create a line that is a vertical line in one of the cross section. So you can see that there is an option called plot over line. You can see my cursor, right? The black cursor is you can see that. So there is a icon here with this plot over, or you can also do. Okay, let me close this and open it again. So okay, now it's running. So you go in the first, you can see in the first row, there is an option called filters, and it will open a drop down menu. So you can go to alphabetical, and when you go to alphabetical, there are so many filters in there available. So you just select plot over line. So it is here, plot over line. In the filters, alphabetical, there is an option called plot over line. So select that. So it will come here, plot over line. Now, where do you want to plot your line? I want to plot in somewhere. Is this the domain length? That the domain width is 65 meters. I want to plot it around 60 meters. So you can see that in the left hand side there is an option called 0.1, 0.2. So you can just type 60 meters in the x direction, and you want your y direction from 0 to 1. So you can visualize here 0 to 1. So it is running from the bottom lower wall to the upper wall. And then you want in the fixed jet plane, that is, let's plot it in the 0 plane, that is in the front plane. 0 means jet is the jet value coordinates 0, which is in the front plane. Now let me click apply. So after this, don't forget to click apply. So now you can see that the velocity u magnitude is ready. Now let's you can see that in the second row there is a place called time, and when you click on this time, there is a drop. There is a 50 written in just left to the right to the time. So if you click that, there will be a drop down menu. So go to the last time step, that is 1000. Okay, now what I want to do is you can while you are in these contours, you can always go to these left hand side and then scroll here. So you can see in this left side there are various parameters, 0.1, 0.2, x-axis, y-axis. So scroll down and you can select here which do we want to plot in these values. So I will just disable p and I want to see the u magnitude. So you can see the u magnitude. Now we can see that the maximum velocity in the rectangular channel flow is always 1.5 times of our the average flow. So if you multiply 0.005 with 1.5, this will give 0.0075. So you can see that at the center, the velocity has reached 1.5 times of our average flow. So by this, you can see say that we have studied that it is 1.5 times, but we can also see it in our simulation. So in a rectangular channel, it's 1.5 times. So I just wanted to show this. So I think you have followed this till now. So you can also plot various results, like you can plot streamlines, velocity vectors, and all these in the post-processing part, but you can do it on your own. So after this, now we need to simulate for the turbulent case as well.
Sir, one question here. Can we extract this data, like this line graph,
Yes,
like you
yes,
plotted
yes.
U magnitude?
Yes, I'll teach you that. Okay, it is possible to extract these data. Okay,
Okay,
so you
thank
can you just search on your own. Okay, I'll now close this in post processing and then move towards the turbulent case. So okay, let's explore the turbulent case now. And now we have already known how to do the laminar case and how to set up our first cell height and the grading values. Now it would be easy for us to set up the turbulent case. So now again, I want you to type open the terminal, fresh terminal. So just open the fresh terminal. But let me close all this. After you open a terminal, you need to type run. Okay, I need to type okay, then type run. You should start from this. Now this will direct you to the run directory. Now I want you to create a new file, new folder called Turbulent. So if I do ls, then you can see that your new folder called Turbulent is being created, right? So after you create the Turbulent, now go to your file explorer and go to your run folder. Okay, where is my run folder? So if you go to your run folder, inside the run folder, there is a new case called Turbulent, but the cases is empty here. So what I want you to do is copy paste from the downloaded code files, all the files into this terminal manually. We won't do it from terminal now, so just copy paste it manually. So go inside the downloaded code files. So inside the k epsilon, so copy this 0 constant and system, and then paste inside the Turbulent folder. Now you can see that when you do it manually, there is an additional file formed, so that won't be a problem here, but it looks bit complex. So okay, so fine. So I think the case is ready now. We just have to block mesh and then run our code. But now let's dive into how we select these values and all this. So you have copied already that part. So that is that means our setup is ready. So what I was showing was just what is the modeling. So we are using Rance modeling, which is the Reynolds average Navier-Stokes equation. So we want to when we average those equations, we get an additional Reynolds stress terms, and we need to model those Reynolds stress terms in terms of the mean flow. So actually the fluctuating flow in terms of the mean flow, and in order to model this, we need the eddy viscosity. We need artificial viscosity called the eddy viscosity, and in order to model this eddy viscosity also, we have different models like the K epsilon model, K omega model, the K omega SST model, and other models are also available. But we will just focus now on the K epsilon model. Okay, so what we want to do is we want to model this eddy viscosity in terms of the K epsilon values, or in the K epsilon model. In the K omega model, we want it to model it in terms of K omega, and the K omega SST model is the blend of K epsilon and K omega models. So I think I don't have much time to describe on what this model is and how this model performs in which type of y plus values, which type of like the which performs best near the wall and the log law region. So you can always refer to the spoken tutorials. So what I suggest you is there is in the spoken tutorials there is an additional file called the if you scroll down, additional reading material, there is a file named additional reading material. So you just click on that. So this will open your PDF. So in this PDF, it is very detailedly explained on what are these models and what are the wall functions, and so which performs based in which type of y plus values. So actually, at a log law region that is y plus greater than 30, a k epsilon is regarded to be effective, and in the viscous top layer, k omega model is regarded to be effective. So if you can choose these models based on the y plus values. So right now we will be choosing a y plus value of 100. Okay, you can see that. So y plus value of 100 means that our y plus lies in the log law region. So in this log law region, when the y plus lies in this log law region, we need to use wall functions in order to incorporate the viscous sublayer. Because when we use y plus very large, that is the first cell height will also be very large as a coarse mesh. So we cannot resolve the viscous sublayer properly. That is the very near to the wall, the gradients, all those things. We cannot resolve it properly because our mesh is very coarse. So in order to incorporate that, in order to incorporate or resolve this viscous sublayer, we need additional wall functions if you select y plus value greater than 30. But if you have y plus value very less in the viscous sublayer, then we can it is not required to use the wall functions. So you can see that in the viscous sublayer, the viscous sublayer is y plus is equal to u plus. So this is you can see that there is a curve here because this x-axis is in the logarithmic scale, so this is a curve. But in fact, this is linear in the linear axis. So and in this region, it is in the linear axis, it will be a curve. So you can go through this, how to what are all functions, how to what are the parameters, all these in these files, and then study detailedly. So now I would like to how to set up these values. So right now we will select y plus of 100. We are not selecting y plus 1 because it will result in a very fine mesh, and then this will also increase the computational time because this and also results in poor mesh quality sometimes. So we are choosing y plus 100. Now after you select y plus, you can see that we can calculate the first cell layer using this formula, first cell height. This yp is the first cell centroid height, not the actual height. It is the height of the centroid. So yp is this value, and the total cell height will be double of this. So you can see that it is calculated here. So using this height, we have calculated the expansion ratio as 15.4. So you can see that if you go to the one that where you have copy pasted these from the downloaded code files, and you go inside the block mesh stick, you can see that the values in the y-axis grading is 15.4. So this is actually this value. So I've also taught you to calculate this on your own using grading calculator. So if you go to this calculator, and the total length is 0.5, number of cells it is 30, right? Number of cells is 30, and you want the first cell height to be, let me see,
It's number of layers here.
no, number of, yeah, you can say that is the number of layers or the total number of cells in that block in the y direction. Okay, so you can see that the first layer, first, that is the cell height is 0.0031. So if I type the first, let me see, with the start cell and 0.0031, so you can see that actually the total expansion ratio comes out to be 15.43. So this value is calculated here using the calculator on our own, but this website will calculate it in the back end. So you need to use this expansion ratio value. So expansion ratio, I have already explained about that. That is the ratio of the last cell to the first cell. So we have used the 15.4, and to calculate this value, just you can alter these end cell and first cell. So you can do this on your own, or you can just do 1 divided by 15.4. So this will also give these values. So just you divide 1 divided by 15.4. This will give this value. So I think the block mesh is also ready. I have not changed anything from the laminar case. I have just changed the grading. So you can see that how grading is done in the simple in these block mesh. There is also options for multi-grading, so you can also look at it later. Okay. So we have selected the y plus in the 100 in the log layer region. So this is done. So we have calculated this. Now we will just look at the KFCL model and we will complete our session. So in order to calculate K, this is the formula. So we have considered the isentropic turbulence such that this gives the formula 3 by 2 U. This formula, you can see that. So the detailed calculation is provided in this PDF. So you can always go back after this session also. So this is for the pipe flow. This is the formula to calculate the turbulent kinetic energy K. So I is the turbulent intensity. So for the pipe flow, it is given by this formula. So here is the calculation provided 0.0261. The value of K is calculated here, and epsilon is also calculated here. So it is very important to initialize these parameters very properly, because this will control, or this will affect the accuracy of our solution. Okay, now we have these values available to us from these calculations. Now we will just use these values in the boundary conditions. We'll do that. So what we can do is, now let's see our case. So go to our turbulent case. Now go to the 0 folder where our boundary conditions are stored. So now you just open the U folder first. Let's see the velocity boundary conditions. So it is just keep as it is. That is a 20 meter per second, because we want a Reynolds number of 200 as 2 million. So from this, when you calculate, we get the average velocity, that is the inlet velocity at 20 meter per second. So inlet outlet, keep as it is. So that is the same as the laminar case. So I want to just show the extra file, that is K epsilon and K epsilon nu T. These are the additional files that are required for turbulent case. So now this is for the epsilon. So let's first see for the K. So you can see that we have calculated K to be 0.4087, which is a rounding off to 0.41. So we have initialized. This is the initial values that we want to initialize our solution with. You cannot choose an arbitrary value, because this will lead to inaccurate solutions and also might lead to divergence. So it is always advisable to calculate it properly. And also the K omega model is very sensitive to these free stream or initial values. So this calculation is should be very proper. Okay, so these and we have seen that turbulent density value is 0.0261. So in order to calculate the inlet, we have so we have calculated the K from the turbulent density, and the value is kept here. So you can look at this. It is available in SRC boundary. These boundary conditions will be located in the source code, so you can see to it. I will show you one. Okay, if at the last, if sometime remaining, I'll show you where these boundary conditions will be available in the source codes. Now outlet will be zero gradient, and you can see that we have used the wall functions, because our y plus is in the range of 30, that is in the log law region. So if you have y plus in the log law region, you need to use the wall functions to resolve the boundary viscous sublayer properly.
So sorry for interruption. There is few details that are different. Like in your case, here it is type. Like in inlet, there is type, intensity, and value. Whereas in what file I've opened, it is type, mixing length, and value is there. And internal field uniform is 0.61 is there.
0.61.
Yeah.
I think you
Internal field.
downloaded it from the 0.61. That you are looking at the epsilon file. That is, I'm
Epsilon file.
showing the K file. That is turbulent kinetic energy.
Sorry.
Okay, look at that. So I'm not going in detail inside these boundary conditions and all this. You can, okay, I'll show you first where you can find these boundary conditions.
Just one question,
Yes.
like in the outlet region, the end there is no end effect. That's why can you tell me the one it is zero gradient over there? There is no value of in the outlet region. So can you tell me the physics at the outlet?
So actually, the zero gradient boundary condition, what it does is it doesn't calculate on the boundary, but it will take the value from the internal cell, that is the cells near to the boundary. So whatever when you solve these equations, that means the gradient is zero in that part.
Okay. Right.
Are located in these like basic boundary conditions are the fixed values, zero gradient. So here is these are the case sensitive. So you can see these are the boundary conditions for the basic and for the constant and all these. Okay, you can explore these on your free time. But the boundary conditions are set here. And also, if you want to see whatever turbulence models are available in OpenFOAM, so you just go to the SRC folder, and there is a folder called momentum transport models. So go inside this, go to incompressible, go to various various turbulence models available in OpenFOAM. So you can go inside the source code, and all these things you can do on your own to explore it more. Okay, now we have boundary conditions available for K. So for the epsilon, this is the boundary condition. So we are defining the based on the mixing. This is the formula to calculate. So 0.07 into L is the mixing length. So our L characteristic length is 1 meter. So 0.07 into 1 would be 0.007. So we have kept 0.007 as the mixing length. And we have initialized the epsilon with the calculated values of 0.61. Okay, and we have used the wall functions. This is required for these cases where y plus is very larger. And nu t also requires the now nu t will be calculated. You can see that nu t will be calculated using this formula c mu k square by epsilon. So it is calculated. We have kept the boundary condition is calculated because it calculates on its own. But the OpenFOAM calculates these values on its own. But we need to assign all the wall functions to these cases also for the walls upper and lower wall, and the front and back is kept as empty since this is 2D simulation. Now after we have the boundary conditions ready, so let's go to transfer properties. Syntax, the keyword used is RAS, and we have the RAS model as K epsilon, turbulence on, and the print and asked to print coefficients. So you can change this to K omega. So you can change this to K instead of K epsilon. You can change it. So you can change it in the turbulence properties file. So after that, the system file. So we have a block mesh dict. I have already explained. I have also taught you how to calculate these gradings, and this control dict. Control dict I have used the simple form, which is a state solver. The time step is not important. It is only kept for the framework because it is a state solver, and the FE schemes FB solution that does it is same as in the previous case. Okay, now let's run the simulation. So let's open our terminal. Run. Now I think you are in the run folder. So first, so what you want to do is go inside Turbulent. So first type run. So you are in your run folder. Go inside Turbulent. Now inside Turbulent, there are these files that we have copied from the downloaded code files. So just type block mesh. This will generate the mesh. So we can see that our mesh is generated. Now, after the mesh is generated, now let's run the simulation using simple foam. So I've also ran the simulation. So you also do on your system. So simple foam, the simulation will stop after the values are converged, or even if we have a larger time, if we have a shorter end time, then it will after the end time is reached, it will stop the simulation. So there are two ways of doing the simulation, but we should ensure that the time step. Okay, after that you click apply. Okay, now again, I need you to repeat the process. That is, let's go to the last time step. Instead of 50, you select there and go to the last time step on that is 1000, and then go to filters, go to alphabetical, go to plot over line, and then you need to plot a line at a distance 60 meters in the x-axis. So you can see that I have kept point 1 in the x as 60, 60. So point 1 and point 2, 60, and y I want to do it in the front plane. So I'll just keep 0. Numerous plots because we have epsilon, k, nu, t, we as well in the turbulent case. So let's first visualize the results one by one. So in this left hand side, scroll down, and you have the option to untick and tick these parameters which you want to so plot in the graph. So first let's just see the u magnitude and untick all this. Okay. So I think the simulation it needs some time more to run because it's quite parabolic. But in turbulent, we have the velocity contour as a flat profile. So we can see that this is quite it's quite near to the parabolic. But after you run some more time, this will eventually change to the flat profile. So because we have already studied that the turbulent flow in turbulent flow, the velocity profile will be flat in comparison to the laminar flow. So after you have visualized the U, so you can see now untick this and see the value of K. So you can see the turbulent kinetic energy. So you can see at near the wall, the turbulent kinetic energy, okay, 0, 1. So these are the plots for turbulent kinetic energy, and if you want to see for the epsilon, and these are the values. So you can just tick and untick these parameters, and in order to export these coordinates, you can click on these side of this layout one. There is option for plus. You just click on plus, and you get this interface. So at the bottom there is an option called spreadsheet view. So click on spreadsheet view, and these and what you want to extract from this simulation. So just click on this yellow icon. You can see here the yellow icon, and here are all options ticked, but we don't want all these options, so just untick them and just tick which is required. If you just want u, epsilon, k, nu, t, and p, so you can just tick these options, and these are the values. Now in order to extract or export this data, at the end there is an option export spreadsheet. So just click there, and you give your file name, give the file location, and click on OK. So you can export these data as well. Okay, so just you can do it plus and in this way, and you can visualize the results and process this accordingly. So what results are important? So you can compare with the k omega and k epsilon as well between these two models. So in order to do the k omega, there I'll just give you how to do that. We have brief overview on how to do it. So go to your turbulence properties. Just set this value. So just set this keyword to k omega RS model, and you need a different file. Instead of epsilon, you need a file called omega. Right. So what I would suggest you is you go to the spoken tutorial website. So there is another tutorial called as that is tutorial number 10. So in this tutorial number 10, in the code file, k omega and how to set up this value. So right now the website, the server is not working, so you can check it later. So instead of epsilon, what you need to do is you need to calculate omega. So to do that, I think I have here. So you can see that omega can be calculated from epsilon itself by using this formula. but the transport equations for this K, epsilon, and omega will be different. The epsilon and omega transport equations will be different, which will be solved in the internal cells. So it will get a different value just to initialize these boundaries to that document in the next tutorial available in the spoken tutorials website. So right now this.
Sorry to interrupt. One doubt I'm facing in the ParaView. My time is till 1 second. Like my simulation didn't run. So what might be the problem? Is it in the like what might be the problem? Like this, I run the block mesh and as well as the after that the paraform. But somehow in the ParaView I can see in the paraform I can see the time is still 1.
So did you copy all the files from the
Yeah,
downloaded files?
yes,
Downloaded
I
code files?
copied the all the transport properties as well as the turbulent properties from the.
No, not just that files. I asked you to copy all those folders from that code file into our turbulent folder.
Yeah, I think I did.
Because I think you have. Okay. So you can open your control dict and match and see there what are the inputs. So just open your control dict. And see if this is the same. Okay, I think now I will take queries and all the issues that you are facing. So if anybody is facing any issues, then you can.
Sir, like in my case, ParaView is not directly getting launched. Like it was problem for yesterday only. So
Yes,
what I
yes.
have to do, I have to put it touch result.form and I have to save it to some other folder, and then from there I have to open ParaView. But
Yes.
this result, when I'm doing, it is showing like multiple option to open. Like when I'm dragging to open, it is showing like a reader.
Okay.
Okay, please.
Okay. So what you do is you scroll down.
Okay,
and
there is a lot of option.
You can see option called open
form reader. Okay, open form reader.
Select that.
But still it is showing error is showing, sir.
What is the error?
Error in C DVD something. Okay.
Okay. Did you copy all the?
Yeah, I have all the 3 files, like in 3 folders. I copied 3 folders from there only.
The time step is also there. Time step folders.
Time step folder. Okay, let me. It will be in a constant, right?
No. And the outside, just inside the directory, turbulent directory. If after you run the simulation,
there are 0 to 1000 times different folders are there. Yes, constants are there. System is there.
Yeah, that thing is not there in my turbulent folder. So, but
my
I
simulation
can
is completed. My simulation is there because I able to see there are 1000 times it was there.
Okay, try what is the form file that you have created? I think the form file is wrong. Turbulent.form, the capital letters, all those. Have you checked that?
Yeah, like I have created the result file as touch result.form. So my result file
you
is
have
like
used
result
all small letters, small letters in form file.
F is capital. F is capital.
No, okay, that's the problem. So just make it small.
Okay. Thank you.
Yeah, I can see the my simulation didn't run like, but my control dict all the steps are like as far as you that you have shown, like in the control dict.
Okay, so have you run block mesh first?
Yeah, I have run block mesh. Yes.
So block mesh is running. Is it fine? It is fine.
Yes, it's fine. Yes. Then I ran the paraform in the turbulent folder.
And simple form. Did you run simple form?
Okay.
Because you need to run the simulation first before visualizing the results. So
I didn't run
this. Okay.
I have one question. Like, how can we simulate, like, animate the simulation that we just performed?
See, if you search on YouTube for ParaView, there are a lot of tutorials available wherein you can learn all of those. I think if you have any other technical queries, you can take that. So demonstration queries now, please don't take that. Take any technical queries if you have.
Okay, okay,
Because how to use ParaView and all
okay.
those things, lot of tutorials are available on YouTube, like saving and all those things.
Like I have like one question. So like if there is multi-physics involved, like I have to solve that like sub ionic fluid is there to transport. So if I have to solve Poisson equation for electrostatics, and from there I have to solve generally I'm talking about perspective for microfluidics. So there will be creeping flow model will be there. So I have to solve
Yeah.
pressure, velocity, and electrostatics is there. So and there is
Okay, so you
coupling,
need
like
to.
body force will be coupled from there because
So this requires a different solver. So we
okay.
can you can use these solvers. There are various solvers in open form. So you just go inside the SRC and see all the available solvers to your problem. So
Okay.
the problem is related to multiphysics and
Electrokinetics, yeah.
problem, electrokinetics. So you will have different solver for these type of problems.
Okay, it's like these files like constant file and zero file, and that will be accordingly
Yeah,
modified.
that
Yeah.
will be that will only be the U folder, P folder. Only the boundary conditions will be modified.
Yeah.
The file structure, the folder structure will be same.
Okay. Okay. Thank you, sir.
So Ismail, for your reference, you can look at our I think last year's workshop in which we had demonstrated electrohydrodynamic cases as well.
Okay, sir.
So
Thank you.
that was a combination where electrohydrodynamics, so electric field, magnetic field effect on fluids, that was also shown, and there we had demonstrated how to write your own custom solvers to solve those equations.
Okay, sir. Thank you. So, like, where
So
I can find that thing, sir?
so the recordings will be available on YouTube. You can
Okay,
search
sir.
FOSSEE's previous. I think it was a 6-day workshop.
Okay,
So
sir.
that recording is available. So in that, Mr. Swapnil had demonstrated that from IITB. So that will help you. It will give you perspective of what can be done.
Okay, thank you, sir. Thank you.
Sir,
Uh,
for LES model, is there any tutorial file like for K omega, K epsilon? There are files. So if I have to
hmm.
apply a model, is there any similar kind of file?
Which model?
LES in the
I
turbulence model,
uh,
turbulence case, if I have to apply LES model.
yeah, you can use. I think the tutorials are not available in the Spoken Tutorials website, but you can refer to other tutorials where you can use instead of the simulation type, you need to set it to LES and then do it accordingly. So you can. This is a different part. This is not run simulation. So you can visit the other websites to how to formulate that, how to formulate those.
Okay.
Okay, I think we need to wrap this up. So thank you everyone.
Yeah, thanks a lot, Mandeep.